Okay, hello everyone. Today we are going to look at we're going to start chapter 2 for our additional math, and in chapter 2 we will talk about mainly on equations and inequalities. So the first thing that we want to talk about is regarding equations, and in 2.1 we're going to start off with simultaneous equations. Alright, so coming from Sec 2, let us do a little bit of recap, and we will explore later on what additional things that we need to learn on top of our simultaneous linear equation from last year Sec 2. Okay, so first and foremost, in Sec 2, simultaneous linear equation means you have a pair of linear equations and the variables are of power 1. Okay, for example, you have something like 5 x plus y is equals to 1, 3x plus y is equals to 2. So what is going on? So this is a pair of linear equation happening simultaneously, right? The variable x and y both have power 1. So this is the first thing that we did last year, and we had 3 methods to solve them. Number 1, it is elimination method, where you can see above, if you were to take equation 1 minus equation 2, straight away you can eliminate one variable. Number 2, second method to solve is the substitution method. It is to take one of the equation, you shuffle the rest to the other side and sub it back to the other equation, so substitution method. Number 3 is our graphical method, and let me show you what do we mean by graphical method. Okay, so let's say if it's a bit different now. So let's say I have something like this, and okay, we have 2 graphs. One graph, we will need to draw like 2 straight lines because these are linear graphs, you know. So we need to draw like 2 straight lines. I'm just approximating. Okay, these are not the exact values. I'm just like roughly drawing the case for you. So last year we draw 2 straight lines, and the objective of this is to solve for the intersection common point. Okay, the common solution or the intersection point. Okay, our common solution. So the common solution usually comes in x and y, like x equals to something, y equals to something, and this gives us the coordinate of the point of intersection for these 2 graphs. Okay, so this was what we did last year. This year we are going to remove, as you can see from the title, right, we are removing the word linear. Okay, we are removing the word linear, and so you can see that now we are no longer dealing with straight lines. Okay, we are just dealing with simultaneous equations in general. And with simultaneous equations in general, we have also 3 methods to solve, but let's examine one by one. Okay, so for example, or before we jump to those things, let us look at 2 examples. Okay, one example would be like, you know, remember your quadratic graph, something like this. Okay, so recently we've drawn quadratic graphs, and we need to let's say I have another straight line passing through this quadratic graph. How many points of intersection does it have? 1 point over here, another point over there, and instead of one solution last time, now I have multiple solutions. Okay, and you can see that it's no longer linear equation, it is one linear and one quadratic equation. So it is one linear and one non-linear equation. Okay, another example that I can give you would be, for example, if we have the circle, okay, equation of a circle, and I have another line, okay, passing through this circle. Same thing, by solving these 2 simultaneous equations, I will obtain the coordinates for the intersection points, or the solutions from doing algebraically will give me the intersection points. Okay, so it is, again, you can see one linear equation, one straight line equation, and one non-linear equation, which is the circle equation. Okay, so over here we have 3, let's look at the 3 methods to solve previously. So previously we had elimination method. So it works because if you look at the example way above, both the x and y, both the variables have the same power, so you can manipulate such that, you know, you can cancel out one of the variable. Now however over here, now you have an x square term, right? For quadratic equations you have x square term, and then you have a straight line x and y. So it is a bit more difficult to eliminate that x, because how are you going to expand such that you know you get an x square and an x at the same time, to eliminate both of these at the same time? So this is one challenging part. Okay, of course you can eliminate y, but it's not going to be straightforward like what we do last time, right? Then for circle equation over here, the circle one, okay, this circle equation, you have both x square and y square term. So elimination may not work properly here, and so we have to resort to the more superior method, which is our substitution method. Okay, so here the superior method is our substitution method. I'm not sure whether like did your teacher say like, you know, the substitution method is the superior one. Okay, it's just that not everyone can do substitution method, so that's why we don't mention this, but it is indeed the superior method. Okay, so when you take one equation, you sub into the other equation, the solution will give you the intersection point. Now next, we also have our graphical method, but the problem with the graphical method, okay, right, the graphical method, okay, we can use this, but the problem with this, right, is that for straight lines we can read the points easily, but for curves, remember last year when you were to plot the quadratic graph, it was a bit of a mess, correct? So the problem with that, and then when you look for the solution or when you look for the roots, it's not always the accurate roots. So the thing about this now is that for graphical method, it will not be too accurate. And as you can see, when you were solving quadratic equation in the previous chapters, we have maybe like square root of 60, square root of 14, square root of 20, that kind of thing. So square roots are irrational numbers, and we may not have our answer in the, you know, the most exact form, the most exact value. So it may not be accurate. So here in this part we will be focusing a lot on substitution method. Okay, so substitution method will be key here. Now, and then let me reiterate one more time the purpose of us doing this simultaneous equation. So when we solve, okay, when we solve simultaneous equations, okay, what do we get in the end? Okay, what do we get in the end is the coordinates of our points of intersection. Okay, between two graphs. Okay, let me put the between two graphs below. So between two graphs. Okay, one more time. So when we solve simultaneous equation, the solution, okay, the solution of x and y, we will obtain the solution x and y, correct? So x equals to something, y equals to something. So this solution will form the coordinate of points of intersection between our two graphs. Okay, point of intersection. Okay, so with this, let's jump right into let's just jump right into the examples in the textbook. Try one. Okay. Okay, alright, so let's move on to the next, you can see try one up here. Okay, so we need to solve for x and y the simultaneous equations. Okay, alright, so yes, so over here we have our try one. So we have our solve for x and y the simultaneous equations, 2x minus y equals to 3 and xy equals to x plus 2y. So obviously 2x minus y equals to 3, like this one, right, is a linear equation because the degree, like the x power 1, y power 1, okay? But however, the equation on the right, we have the x, 2y, all these are power 1, degree 1. However, xy, because we have two variables together, degree 1 times degree 1, you actually get a degree 2. Okay, so now it is a linear and a non-linear case. So I know that it may not make sense for now, but let me show you graphically what does it look like. Oh wait, I want to just solve for you first, then I will show you graphically what it looks like. Okay, so over here we have our try one. Okay, try one. Okay, let me pause for a while. Okay, and try one is on page 28, right? So over here, alright, so let's do this. We are going to start off with the first equation. So 2x minus y is equals to 3. So I'm going to like make y my subject, right? So this would be my equation 1. So I need to prepare y as the subject to sub in later in the second equation, right? 2x you can, but you know you need to like get rid of the 2 in front, and then you get a fraction, which is not so nice, okay? But sometimes really no choice lah, okay? Next one, equation 2, we have our xy is going to be equals to x plus 2y. Okay, so I'm just going to let this be equation 2. So I will just need to sub equation 1 with equation 2. Now one more time, we want to remind you, ever since last year, label your working carefully. Okay, so we have our substitute, right? Equation 1 into equation 2. Okay, label properly. So we have a x times y, and y is 2x minus 3 equals to x plus 2y. Again, 2x minus 3. Okay, so we expand, so 2x squared 3 minus 3x, x plus 4x minus 6. Okay, notation, be careful of the notation there. So the bracket notation, yeah. So the quadratic equation, because this is a quadratic equation, 2x squared and so on, I'm just going to make everything into what they call general form so that I can solve easily. So 2x squared minus 3 minus 1 minus 4, so minus 8x plus 6 equals to 0. All are even number. Let me divide by 2 to make my life easier. Plus 3 equals to 0. Okay, so with this, it looks factorizable, so I'm just going to go and factorize x minus 3, x minus 1. Okay, so x is going to be equals to 3, or x is going to be equals to 1. Okay, so now the problem is I have two separate solutions. Okay, two separate solutions, and because I have two x's, I need two y's. And where can I get the y from? I can get from 2, but it's not going to be convenient, so I'm just going to use 1, equation 1. Just nice, the y is there. So I'm just going to write from equation 1. Okay, from equation 1, y is equals to 2x, right? 2x plus 2x minus 3. Okay, so y is equals to 3 here, or y is equals to 2x minus 3. So 2 minus 3 will give me negative 1. Okay, so my final answer, because I have my solution, so my solution, right, would be x equals to 3, y equals to 3, or x equals to 1, y equals to negative 1. You can like list them vertically, or you can list them horizontally, also can. So you can see, right, 3, 3, x3, y3, 3, 3, the point 3, 3 is one of our intersection point. The point 1, negative 1 will be our second intersection point. Okay, so with this, right, let's let's give you a pictorial view. After doing all this algebra, right, what do we really mean by this? Okay, let me pause for a while. Okay, alright, so let's take a look at, now we have the graph. I'm going to use Desmos. Okay, Desmos is our good friend for graphs. Okay, so the question over here, we have 2x minus y equals to 3. It's going to be a straight line, so I'm just going to type in, you know, like 2x minus y equals to 3. Straight line graph. Okay, confirm straight line graph. Now the second graph that I want to drop in would be this xy equals to x plus y. So just curious, I don't know whether are you curious on what this graph looks like, but anyway, x plus 2y. Okay, so this graph looks like, you know, a curve like this and like that. We called it a hyperbola. Okay, a hyperbola. Hyperbola. Okay, so what is going on is this green color. Okay, I don't know whether you can see the color now. This green color line, okay, is intersecting with this red color. No, red is not good colors. Yeah, this blue color curve. Okay, and where is it intersecting? At two different points. Can you see the coordinate? 1, -1 over here. The other one here would be 3, 3. Okay, so intersecting at 2 points. So this was what our solution mean earlier. Okay, this was what our solution mean earlier. X33, no, as in the first one is 3, 3, second one 1, -1. It actually means, like, you know, that two intersection points that you can see over there. Okay, so this is our first question. Try 1. Okay, so ready? So this one will be holding substitution as key to solve simultaneous equations. Okay. Alright, let's come back to this. The thing is, right now, how do I should go there. I should put here, right? This one, this one I should go upwards and see. Okay, I think this, okay, alright, whatever. Okay, so, oh dear, middle. Okay, a bit lah, can. Okay, can. So next one, the next question we have would be try whatever. Okay, second question, try 2. Okay, I think try 2 is the next page. Try 2. Which page is try? Whatever lah. Just now was 28, right? So I think like one page 29. Okay, can. I think roughly either 29 or 30 okay. Alright, so for try 2, we have the coordinates of the points of intersection of y minus x minus 3 plus 3 equals to 0. Okay, and the other one is x squared minus 4x plus 1. So we take, before we start, right, let's take a look. So the thing is, we have x squared and 4x. We'll probably need to solve x. So I will need to make y the subject for this equation. So y on the left, the rest on the right. So this will form my equation 1. Okay, equation 1. Next, the curve y is going to be equals to x squared minus 4x plus 1. This is going to be my equation 2. And just nice, y equals to y. So technically, 1 equals to 2. So technically, we are substituting y, but we also can put 1 equals to 2. Okay, so we have x squared minus 4x plus 1 is equals to x minus 3. Tidy up, 5x and plus 4. Looks like you can factorize again. Minus 4 minus 1. So x is going to be equals to 4, or okay, leave some space, or x is going to be equals to 1. Okay, so this is my solution for x. I'm going to look for y. I'm going to need to borrow equation 1. So from 1, y is going to be equals to 4 minus 3. So x minus 3. Y is 1. So y is going to be equals to 1 minus 3. So this minus 3. So this y will be negative 2. So therefore, the solution is, I can put x equals to 4, y equals to 1, or x equals to 1, y equals to negative 2. Right now, they are asking for coordinates. Oh, they are asking for coordinates. So I should be, yeah, so the answer would be 4 and 1. Okay, and the other one would be 1 and negative 2. Okay, so these are our points of intersection, the coordinates. Okay, so let's double check and see how we are like for this question over here. This one though. Okay, alright, so over here we have our two equations again. Let me type in y minus x plus 3 equals to 0, my first line. My second line would be y equals to x squared minus 4x plus 1. Okay, so as you can see, we have intersecting with 2, 1, negative 2, and 4, 1, like our solution there. Okay, 4, 1, okay, 4, 1 and 1, negative 2. So in the graph, it's also 4, 1, okay, 4, 1, 4, 1 and 1, negative 2. Okay, so just nice. Okay, so this is equation 2. Try 2. Okay. Okay, alright, let's take a look at try 3. Okay, the third example. Okay, try number 3 on the same page. Okay, try 3. So we have a rectangular frame. So now we are applying it to a problem in real world context. Okay, and we will need to model this problem into probably two separate equations, and we will need to solve them accordingly. Okay, so we have a rectangular picture frame, area 154, perimeter 50 cm. Find the dimensions of the picture frame. Okay, so before we model, let's draw a model. Okay, before we do anything, we draw. Hello, my box function, not square function. I want box function. Okay, just nice. Okay, so dimensions, because I'm not too sure, and then we have two separate dimensions. It's a rectangular picture frame, so I'm going to just do like A and B, just in case. Okay, A and B. So area 154 cm square. So area AB is going to be equals to 154. Okay, equation 1. Okay. Alright, AB equals to 154. Now the perimeter. So how will I look for the perimeter? Would be 2A plus 2B. Okay, the perimeter is given by 50 cm. So just nice 2A, 2B, right? I can divide by 2. So A plus B give me 25. So I will take A would be equals to 25 minus B. So this is my equation 2 over here. Okay, so as you can see, I need to form the relationship first and then form my second equation. Then how do I do next? Would be sub 2 into 1. So sub equation 2, okay, into equation 1. Okay, substitute equation 2 into equation 1. So I will have my A, which is 25 minus B times B will give me 154. So 25B minus B square equals to 154. Change to general form because now I have a quadratic equation. So B square minus 25B plus 154. Let me quickly check with my calculator and see what kind of solutions am I going to get. Okay, 14. So means it is factorizable. So this one would be, okay, B minus 14, B minus 11. Okay, so therefore B is equals to 14 or B is equals to 11. Okay, so with this one, right, so what is A? So from equation 2, right, A would be equals to 25 minus 14. Sub the 14 there. So 25 minus 14 is 11. Same thing lah. So 25 minus 11 give me 14. So actually they are the same. Okay, actually both solutions are the same. Okay, now I need to move this over here. Move myself to the other side. Block less. Okay, so we have this situation over here. We have A is 11, B is 14. So it's one or the other one. So therefore we don't need to like solve. We don't need to like say A and what B and what for this case, because I think the question is not interested in this. The question is just interested in dimension. So the dimensions, okay, for this picture frame, okay, will be equals to just 14 cm by, or you can just by 11 cm, just like that. Okay, so there we go. Okay, over here, an example of using simultaneous equation to solve, okay, a real world problem. Okay, and we model it by, you know, area, perimeter, and then we assign variables, form the relationship, and then solve algebraically. Okay, so that's all for 2.1. So the main idea, once again, the main idea for this one is, now you have simultaneous equations in general. May not be two straight lines, maybe one straight line and another curve. So how do we solve them? Substitution method is the powerful method that we need to know for this one. It can solve almost any simultaneous equation. Okay, so with this, why do we solve for simultaneous equation? Of course, is to solve like real world problems like this, but the bigger purpose is to find the point of intersection between two graphs. Okay, and then we use simultaneous equation to find these 2 points. Okay, so with this, let me end the lesson, and to wish you a good HPL day. Okay, bye bye.